So we are interested in developing this photo desalinator, and in this device we can use a photo-assisted catalyst for the oxygen evolution reaction. Here we have used electrochemical catalyst formed from molybdenum disulfide. In the middle, we can use silver membrane selective for exchanging cations and anions. And we can put it on seawater for the desalination. In this part, we can use acid wastewater for the reaction here, for the production, hydrogen production. And the other side, we can use alkaline wastewater. So the voltage applied for this device can be decreased. And it's a way to the treatment of wastewater. But in this presentation, I'm going to talk about okay. But in this presentation, I'm going to talk about the hydrogen evolution reaction, okay? And we have used amorphous molybdenum disulfide. Because this material is no expensive and is stable in acid medium. And Jaramillo's groups has shown the high catalytic activity for hydrogen evolution due to the molybdenum sites at edges for the crystalline molybdenum disulfide. But in our case, we have used amorphous molybdenum disulfide because the sulfur sites can participate of the hydrogen production. In this case, for the synthesize, we have used molybdate, ammonium molybdate, and sodium sulfide and aqueous medium. And we have used several techniques, in this case, microscopy to investigate about the morphology. And here we can see the morphology before and after the electrochemical treatment. So we have obtained the bidimensional network of molybdenum disulfide, amorphous molybdenum disulfide. So we can observe the high surface area. We have done other techniques, XPS, SVM, and EDS for the characterization about the elements and the oxidation state of these elements before and after electrochemical treatment. So here we can see the experimental linear sweep voltammetry and the, for several linear sweep voltammetry. And we can observe the increase of activity for the hydrogen evolution. And this is the linear sweep voltammetry at 20 millivolt per second for several rotation frequency, different rotation speeds, okay? And we have used, we have done impedance measurements to investigate a better understanding about this reaction. We have considered for the hydrogen evolution reaction 2 steps for this case, Vollmer and Heirovsky steps. So we have done the expansion about the Faraday current density oscillatory Faraday current density as a function of overpotential, surface coverage degree, and the oscillatory hydrogen concentration at surface. We have considered the Butler-Volmer equation and the Langmuir isotherm. So here we have used that expression of Butler-Volmer and Langmuir isotherm, and we have done firstly is necessary to do this derivation. Okay. In this case, it is necessary to investigate about the surface coverage degree as a function of time and frequency. Finally, it is necessary to obtain the analytic solution for the oscillatory hydrogen concentration at surface. So we have used Fick's laws and initial and boundary conditions. And we have obtained this transference function, this Faraday impedance. And we have coupled the double layer capacitance. And we have used that model to fit these Nyquist diagrams for the several rotation, several frequency rotation. And we can observe the resistance, charge transference resistance, the impedance associated with the surface coverage, and the mass transfer impedance. And we have fit the body diagrams for the same rotation speed rotation. Based on this fit in this model, we have obtained these fitting parameters over potential. This is the associated with the Schmidt number, cinematic viscosity, the double layer capacitance. We can observe the high capacitance of this double layer, this kinetic constant degree, surface coverage degree for this potential, and the diffusion coefficient of the hydrogen, molecule hydrogen. In this case, we have proposed this method because in this case, we have separated the mass transfer impedance from the other impedance in that diagrams. So we have considered just the mass transfer impedance at frequency zero, i.e. At frequency domain, time domain, okay, where frequency tends to zero. So in this case, we have considered the nesting behavior, reversible behavior. So we have used the nest, but considered the infinitesimal change for the concentration, hydrogen concentration at interface, and Levitt equation. Because of this, it is possible to determine the hydrogen concentration at surface at steady state on basis of the slope of this line. Okay, and in this case we have we haven't considered the impedance associated with the irreversibility about the charge transfer impedance. Okay, and we have used this expression associated with this irreversibility to decrease of the freedom degree, because this is a fitting, so it is necessary to decrease the freedom degree. So on basis of this method, the freedom degree tends to 0. Here, I show the inverse of experimental current densities as a function of the inverse square root of the rotation frequency at several potentials. So we have used carbon glass rotation, and on basis of the slope, we have obtained the diffusional current density, because we have the control of the hydrodynamic thickness. And we can observe the same value for the diffusion current density and the experimental current density. So the process is limited by the diffusion process of the hydrogen at surface, from surface to bulk solution. Okay, and on basis of the linear coefficient, we can determine the kinetic current density. So these points correspond to the kinetic current density, i.e. the Butler-Volmer profile. And this green line corresponds to the theoretical data on basis of the impedance model. On basis of these fitting parameters and the experimental results, it is possible to determine the hydrogen concentration at surface as a function of potential. And we have obtained this profile at surface. Okay? And we have used the first Fick's law. On basis of numeric solution, it is possible to determine the concentration profile of hydrogen in the hydrodynamic layer as a function of the potential. This is the coverage surface coverage degree as a function of a potential, where we have used the Langmuir isotherm. And here we have the logarithm of current density, experimental current density, diffusional current density, kinetic current density, corrected current density, and the kinetic current density associated with the impedance measurements. So, on basis of these results, the conclusions for the first part, it's a turnover frequency is close to 0.001 hydrogen per second per surface site at the equilibrium potential, but at 50 hydrogen per second. This is very high. The exchange current normalized by the geometric area, and the catalyst surface area are very high, also very high. The ruggedness factor of the catalyst is 116. The Tafel slope is close 49 millivolts per decade at 71 millivolts. It's very small for this reaction by using this electrochemical catalyst. And this is an important point because on basis of this slope, the mechanism proposed is correct, is associated with this Tafel slope. So this mechanism is close to the esperado. So the Hayrovsky step has been identified as the rate limiting step for the kinetic current, while the diffusion convection of molecule hydrogen limits the reaction. So this is the first time I have how long time at this moment? 10 minutes, 15, more. Okay. Okay. In this case, we are interested in developing the electrochemical system to harvest the energy during the treatment of wastewater, of acid wastewater. So in this case, we have used 2 electrodes, and these electrodes are selective for the specific ion. So here we have used polyoxymetallate and other electrode specific for adsorption or insertion anions. So in this case, we can put it on acid wastewater, and after we have used a battery or capacitor to promote this proton insertion or proton adsorption in this electrode. In the other case, there is the insertion or adsorption anions on the positive electrode. After, we can put it on alkaline solution for the neutralization process. And the last step, there is the spontaneous process. So in this case, there is the charge process, non-spontaneous. In this case, there is the discharge process, spontaneous process. So after this cycle, it is possible to harvest the energy during the neutralization acid wastewater. We can understand this process from thermodynamic point of view, because in this case, we can remove ions from the concentrated solution during the charge process, and after the neutralization process, we can put it on these ions in the diluted solution. So we can understand like a mixture free energy, but the main contribution for this free energy is associated with the entropy change in the entropy, like a concentration cell. From electrochemical point of view, we can understand by using the Nernst equation, consider the equilibrium state. So the decrease of pH, the voltage is low. After the neutralization, there is the increase of voltage because these reactions are specific for the ions. So we can understand with this figure. Here we have acid, and there is the charge process. After the addition of alkaline solution, there is the discharge process. So this area corresponds to the harvest energy, the energy harvest after the electrochemical cycle. And we can use the thermodynamic to determine the maximum efficiency because the free energy corresponds to the maximum free work. One of the properties to use electron is the practical reversibility. This is very important because the irreversibility corresponds to the dissipation of heat and not work, electrical work. We have used as the phosphomolybidic acid in one of electron. Other important property is the selectivity. So it is necessary that the electrode to be selective for the adsorption-desorption protons. And we can observe this behavior by using the change potential as a function of pH in the equilibrium state. And on base of this slope, it is possible to observe the participation of the protons. We have used electrochemical quartz crystal microbalance, and on basis of the electroneutrality and mass conservation, it is possible to determine the participation of cations and anions during the electrochemical process. Here, we can see the change of the potential window as a function of pH. So we can observe that the charge process, after the neutralization treatment, the potential associated with the oxidation is in the negative potential. So because of this change, we can obtain the energy after the electrochemical cycle. And we have done the proof of concept. Here some results and some data about the work produced or stored by using this electrochemical system. And here the efficiency on basis from thermodynamic concepts. And during the neutralization process, we can put it on alkaline ions. So we have used, in this case, analog Prussian blue to harvest the energy from the change in sodium and potassium ion during the neutralization. And we have used thermodynamics, and this is the morphology for the polyoxometallite, and some results, and we can observe the change of potential and associated with the reduction and oxidation as a function of pH. Here, we have observed the chronopotentiometric curves for these materials for several pH. This figure corresponds to the efficiency of this system in comparison with thermodynamic data. And for this, to investigate about the kinetic process, kinetic studies, we have used impedance. And in this case, we have considered only the charge transference and adsorption hydrogen at surface. So we have used Langmuir, isotherm, and Butler-Volmer for the at steady state and at the oscillatory state. And we have considered the surface coverage degree as a function of time and as a function of frequency. So we have obtained the relation between oscillatory coverage degree as a function of oscillatory potential. So this is very important because we can substitute that expression here. So because of this, we can determine the Faraday impedance. But in this case, because the material is porous, we have considered the behavior associated with the porosity. So we have used the line transmission. And for me, this is one of the best model to associate it with the fundamental electrochemistry fundamental, yes, kinetic study with mechanism reaction mechanism, because we can substitute this transference function for this transmission line. Because we can substitute this expression in this here. And the other part of this function is associated with the porosity, because this is a three-dimensional material. So the field lines is different from the planar electrode. So in this case, we can analyze the kinetic of the reaction, and it is possible to incorporate the effect associated with the distortion of electrical field. And here, this is the experimental and the theoretical data for the polyoxymetallate. And we have used the same concepts for the Prussian blue analog. And here we can observe the porosity for this electrode. And we can observe the dependence of potential as a function of sodium concentration, because in this case, there is participation of cations to increase of the energy after the electrochemical cycle. Here, we can observe this analog Prussian blue is not sensible with the pH of the solution, because the participation, the intercalation is associated only the sodium and potassium ion. We have used Debye the vehicle and expanded the vehicle to determine the activity for this solution. And because of this, it is possible to determine the maximum energy harvest after the electrochemical cycle. This is the chronopotentiometric curves, the efficiency of this material from experimental and thermodynamic prevision. For this case, we have used the similar concepts, but in this case, we have considered the charge transference and the diffusion of sodium and potassium ions into this intercalation electrode. So this is the function. It's more complex because of the mass transference, and we have used this transference function in the line transmission to considering the porosity. Yes, here. So this is some fitting of these materials of this experiment. In this case, we have considered a three-dimensional plot because it is necessary to investigate about the imaginary and real part of the impedance and the frequency. And here we have some results, some parameters obtained of this fitting. And finally, here, this work has investigated of this material associated with this proton adsorption and potassium and sodium ion intercalation. And we have used techniques and models on the time and frequency domain. And this system can be used in the Coase dilution and neutralization process to harvest the energy. This low practical reversibility corroborated by the rate constant values determined from the measure and kinetic model in the frequency domain. And so in the final, the resulting energy harvest and power density corresponded to values around the 13 kilojoules and the 40 watts per mole of adsorbed proton. So thank you. I'm grateful for this opportunity. Thank you for attention.
Thank you very much. I'm sorry, I need to borrow your microphone to ask everybody for, it's the only one we have, the other collapsed. Ask the audience for questions. Anyone? Yes. Take care of the microphone.
Thank you very much for the presentation. Very interesting. There's a lot of information that you pass very fast, but there's a lot of information. I have a question about this battery. The fact that the model is amazing, but in terms of all batteries, have you considered or how you're considering or working with the internal resistance to how at the end, because this is a theoretical maximum, of course, but in the reality, the prototype you assembly or which are the deal or what are you finding about the internal resistance of the own cell, how it affected?
Microphone. Thank you, Danny. In this case, we have considered the Faraday process. So after these models, we have to couple the capacitance, and the internal resistance is only to the real part. So the everything is we have subtracted, yes, the internal resistance, but it's no problem because the internal resistance independent of the frequency and time instantaneous. So the first points, it is possible to subtract of the all results.
But my question was the experiments you have done, which is the internal resistance you have found in your setup.
How can consider this resistance to obtain the assembly battery? In this case, theoretical, we can add this resistance, but in the practical, the theory doesn't work. But the model is important because we can do the expectation, yes, but not the same.
Realization.
Yes.
No, but that
Yes.
is always clear with models, I guess.
Yeah, models and models.
Yeah, that's okay. Everybody understands. I have several questions. If nobody is ready to ask, okay, yeah. I'll ask last.
Thank you, Fritz, for your presentation. It's concerning the first part related to MoS2. I'm a little bit confused about how you consider your material a 2D material, and actually I have two. And the second one, if you expect something different.
Two questions?
Yeah.
No, just one after. English is not.
Complex. It's a question, the Brazilian from Brazilian, because I'm also Brazilian too.
Yes, we don't have the national languages, so it's hard. So the question is, how can we understand, how can prove about the activity?
So how you said that you have a 2D MoS2, right? But you just show us SEM.
Okay.
SEM is not a real technique to prove this.
Yes.
So
okay.
how you can show that? How you can see that it's real 2D material?
A single layer molybdenum sulfide.
Yeah.
Or something.
Yes, because this is one of this motivation to be here. It's this a presentation and the collaboration with Pedro. So I brought the sample to investigate about this.
Okay, so you don't have the real idea that you still have a 2D material, or you have?
Yes, I said it to bidimensional network. Yes.
Yeah.
Only based on this figure, born in this figure.
Okay.
But it's necessary to investigate. But this question is very important because during the, wow, too much slides.
Yeah, you see, we said much information. What I would say is high level of information density. Normalized.
With this presentation was in Portuguese or Portunhol, just 10 slides. No. But in English, it's necessary to put several slides. Yes. Olha só.
Yeah, that one, yes.
Based on this figure, but during this experiment, the filament of the microscope broken. So this image was very important because during the model, we have observed the high capacitance. So when I saw this image, I could be the high exposure of the active of the sites. Yes, but it's necessary more refinement about this morphology. But this is very important because the number of active sites for this kind of materials is not so high. So it is necessary the high surface area. But in our case, there is other important point because the turnover frequency is very high. So this kind of materials is necessary the frequency of reaction to be very high because the number of active sites is low. But in our case, we have the high turnover frequency and the high exposition of sites.
Right.
And because of this, the process is limited by the diffusion process.
Mm-hmm.
We can observe this, no only the model, but the experimental data. Look at this. We have changed the rotation speed. We can observe the change in current as a function of the speed rotation speed. So this is indicate the dependence of the current with the diffusion process at low overpotential. It's before the onset potential. So the process is limited by the diffusional current density in the initial. This is the lime green. Oh, sorry. Here. This is the Butler-Volmer without mass transference. So we can observe the low overpotential. There is the activation process. The limitation about the charge transference occurs at low overpotential.
Okay. Yeah, the question was the two-dimensional nature, how many layers, and this is still to be maybe determined and optimized. And the second question?
The second is, you said that you have an amorphous materials, right? What do you expect if you change the amorphous for a crystalline material like a 1T, a metallic MoS2?
Oh, that was my question.
Sorry about that.
1T is fantastic materials, but we are discussing yesterday about this catalytic activity.
Mm-hmm.
So IT is very good, but it's not stable. So IT has several defects, and there is other sides different from the molybdenum through age. Yes.
Other metals, so that possible
Yes.
impurities and so on.
Yes. And other point is about the conductivity. The conductivity is very different when you use IT. It's better, yes. But high activity, but is not stable. And amorphous, there is several defects, and there is the participation of British sulfur in this adsorption, hydrogen adsorption.
Mm-hmm.
And these are these effects have been observed by using XAS.
Actually, it would be most interesting, even necessary, to do the same fitting for data from single layer crystalline moly disulfide, which we don't have, unfortunately, but if anyone got some
You can do the
Yes, yes, a conventional procedure, but yeah, but it would make sense to compare both. Yes. More questions? Yes.
Hi, I have some questions about the Tafel slope. You mentioned that it was around was close to 59, no 49 at some potential, but at higher potential it was close to 120. So do you have an idea why it is changing?
Because here we have the experimental. The point is the experimental based on the rotation of electron. And these are theoretical. And because of the impedance measurement, it was possible to determine, because the reaction is limited by the diffusion, but the impedance separates the process. And your question is about this slope and the surface degree. No surface degree. Yeah. The slope is 49 millivolts per decade, and this is typical for the Volmer-Heirovsky and limited by the Heirovsky. But for the high overpotential, this surface degree tends to 1. Yeah. So the limit rate is Volmer, no more Heirovsky. The constant rate constant is higher for the Volmer, but because of the free sites decrease because the high surface coverage because of this.
Thank you for your presentation. It is nice to see you. I am Ceren. I wonder that did you try to compare these results with the commercial catalyst, for example, platinum carbon? Do you have these results with you? How is the effect of using that material? Thank you.
Thank you, great question. I have to, my student, Bianca, has obtained these results 2 years ago. And during 1 year, I have to investigate about these models because these results is unbelievable. The best results for the system is come back here. Here it's okay. The best onset potential for these materials is close to minus 160 millivolts versus hydrogen reversible electron. In our case, is close to 60. Is very, very low. Because of this, we have to investigate several parameters. And now I bring the sample for more investigation because it's very, very nice. But when we compare with the platinum, it's impossible because platinum, the Butler volume is close to zero, and the slope is low, yeah? and the overall potential is low, and the platinum is the best catalyst for this reaction. But we know about the price, the cost, so this is a problem. And this material is a possible application for that, this photodesalidator. And we have other properties. It's about the contamination. Platinum is poison.
It's poisoned
with
by
several anions and
carbon, no?
organic. But these results is very good for us.
Okay. And probably if instead of platinum we get some carbon, then this would be better in overpotential and in diffusion limitation. I really appreciate that. It's a great result because it's telling us that the more surface you have, imagine we could devise a three-dimensional porous electrode, and you would get lots of hydrogen. So it's telling us that there is a great potential with this material.
Yes, and this indicates that this limitation associated with the diffusion process indicate the high turnover frequency. Because the number of active sites is not so high like platinum. So this is possible because the high surface area, no geometric, but real,
yeah.
and the high turnover frequency.
Yeah.
So this experiment corroborate about the model.
Yes, absolutely. But let's say that from my point of view, material science expertise, I really want to know more about the material. You have made a physical, chemical, excellent work, but we need, as material scientists, right? We need to know what makes the difference. First, to show that there is a difference with a crystalline, long-range order 2D moly disulfide, and then understand why the difference. Because we have discussed a little bit about it, but maybe too short. But it was, you mentioned the amorphous having more defects, strain maybe. I mean, there is plenty of room to research this material, regardless of whether it is truly 2D or few layer moly disulfide in an open porous. Okay, so I think is very, very nice work. I had that question and another one, which we have also discussed, but I think it would be worthwhile for the audience to listen to my my thought about the second half of your presentation. We have a saline battery. We have acidic, basic, and out of the entropy component of delta G, we get energy, right? And from the beginning, remember, I told you, well, but it would be wonderful to do it the other way around. What if you use energy to separate salts and make some kind of purified water? That is, could we compete with inverse osmosis for purification of water? So I would like you to share your thoughts about this.
Yeah, because the entropy, it's a form, a way. We can harvest the energy for the entropy, but the energy is like a degraded way energy. Yes, so we can use just one time. Yes.
Yeah. One shot. You mean?
Yes. Yes, but we can harvest the energy for the entropy.
No. Yeah. Okay.
Yeah, and so this application is just for the open system.
Right.
Yeah. It's impossible to harvest the energy from the closed system.
Right.
And it's how can I say in English? Energia desperdiçada.
Wasted energy.
Yeah.
Yeah.
So we can harvest from this
Right.
because nobody harvests this kind of energy.
Right,
So it's a possibility.
Yeah,
Yeah.
exactly. Waste to us is equivalent to disposal.
Yes. So because of this, it's it's harvest the energy. Yes, it's a little energy, but we can use these two electrochemical system because we can use the acid-base machine and desalinator to obtain water from the acid and alkaline wastewater, and we can obtain energy because everything is obtained from the sunlight.
Right. Yeah. Well, of course, the primary source is always the sun.
Yeah.
Okay. Well, thank you very much. If there are no more questions, join me in thanking Fritz for this very interesting presentation. And well, welcome.